Hello and welcome back to a new chapter. We started with the most basic passive component, which is resistor, and after that we studied about capacitors, right? And we combined theory with some practical examples, but now it's time to take this to a step further and see what can we do when we combine these two passive components together. So let's get started. Do you remember about this circuit? Of course you do. So when I hit the switch, there will be a current flowing in this path, but a DC current will flow only until the capacitor is charged up and the voltage across the capacitor will be equal to the voltage of the battery. Let me stop the simulator so that our voltage and current graph will stop moving. Now, when we charge a capacitor with a voltage level, it's not surprising to find that it takes some time for the capacitor to adjust to the new level. Exactly how much time it takes to adjust is defined not only by the size of the capacitor, but also by this resistance in the circuit. The RC time constant, which is measured in seconds, is a measure that helps us to figure out how long it will take a capacitor to charge to a certain voltage level. The RC constant will also have some handy uses in filtering that we will see later on. So calculating the RC time constant is very straightforward. Just multiply the capacitance, which is in farads, by the resistance, which is in ohms. Remember to take care of your powers of 10, because for example a microfarad is 10 to the power of minus 6 farads, while picofarads is 10 to the power of minus 9. If we multiply 200 microfarads with 100, we will get 0.02 seconds. Does this mean that the capacitor needs 0.02 seconds to charge from 0 volts until 5 volts? Well, not really, but we wouldn't be very wrong either if we say so. Here's an RC circuit getting charged with 10 volts DC source. Assuming the capacitor started with 0 volt, its rise of voltage over time will look something like this. The key point here are to note that after 1 RC, the capacitor will have reached about 63% of the input voltage, and after 5 RCs, the capacitor will be very close to the input voltage. So in the previous circuit, our RC time constant was 0.02 seconds, right? So multiplying 0.02 with 5, we get the time needed for the capacitor to fully charge. Cool, right? Now, if we change this DC 10 volts power source to ground, then the capacitor will discharge, right? And here again, the discharge time would be determined by the RC time constant. The RC curve for discharging looks like this, and the key points on the discharge curve are at 1 RC, where the voltage is about a third of the original, and at 5 RC, where the voltage across the capacitor is nearly 0. Here's an exercise for you. We have this circuit here, and it says to find out the RC time constant. The time constant, as we know, is equal to R times C. So 47 kiloohms times 1000 microfarads is equal to 47 seconds. This means that in 47 seconds, the capacitor will be charged at 63% of the input voltage, and it will take 5 time constants to fully charge.